Now, again, real systems, real thrust fold belts are going to have a mix of the duplex and the imbricate fans because the real world doesn't like doing things neat and tidy. It does it however the rock breaks and bends. So this is a nice satellite image from Google Earth of a thrust fold belt. You can see this is in Mexico, right near Monterrey. And you can see all of these beautiful folds. Here's a cross section going across, so basically in kind of a north-south direction. And you can see this right in the middle of this cross section is the big thrust fold belt. Actually, my mistake. This is a cross section of a thrust fold belt, but it's not the same one. I forgot when I found this, I didn't have a cross section of this thrust fold belt. But you can see how this cross section would look very similar to what you see right here. But yeah, this thrust fold belt cross section is actually from within the United States at the West Virginia border. So there are 4 broad categories of thrust folds that I want to look at, looking more small scale, what's going on. We can have folding associated with brake thrusts. So we've got, it's folding, more and more compression. The rock hits its limit of plastic deformation and breaks, and you get this thrusting reverse fault forming. This one looks to be actually a reverse fault, not a thrust fault. The angle's a little bit too high, but the break could have happened at any angle. And you can see here that the fold remains. We can have the bending, the folding, that relates to a ramp in a thrust fault. We have a back arc limb, basically the side of this anticline, that is not the leading edge, so to speak. The forelimb is the leading edge. This is the direction of motion to the left, and so this forelimb is the leading edge of this anticline. The back limb is the one that's parallel to the ramp. It's the one going up currently. And if the fault doesn't reach the surface, but it grows over time, we get a lobe of an imbricate fan. So this is a fault propagation fold. So as this fault tip moves upward, the fold grows. You can see the progression from time 1, time 2, and time 3 on the bottom right. The fault is now cutting through more and more layers, still not reaching the surface. And to form an imbricate fan, this fault will never reach the surface. This fault tip will actually die out, and a new fault will start to the left of what's shown here. This is an example of that fault propagation fold. The compression was basically from the bottom right to the upper left direction, and you can see this very zigzaggy appearance from all of these fault propagation folds. This image is from the publisher, and this image is in your textbook. However, in your textbook it isn't all pixelated like this. This is the second time, if you remember back when we were looking at the cross-section of the oceanic crust, there was one all pixely like this. I'm sorry. This is what the textbook publisher provided. I don't know why. However, you can still basically see these layers that are folded in the top, and down in the bottom it is not folded. It looks kind of wavy, but that just happens because of the pixelation. The idea is that this big detachment separates folded rock above the detachment from unfolded rock below the detachment. So this is detachment folding. This top is sliding and compressing and folding, where the bottom just hangs out and does nothing. Now, an important thing here is notice the direction of motion. This is not a ramp like we've seen in all of the previous slides today. The motion is going down the ramp, not up the ramp. But we still have lots of compression. We even have some faulting up in this detached area. This is a very thick layer of rock. This is sea level, 400 meters above. So going as high as maybe 600 or 700 meters above sea level, going down to about 400 meters below sea level. So this is pretty thick, over a kilometer thick in places, less than a kilometer thick in these valleys, of detached rock that is sliding across the basement rock, and it is folding, but the basement is not. So we've looked at the regional, we've looked at within a single fault in a single fold. We can also look at the microscopic scale. So we can go from mesoscopic, huge, down to microscopic, tiny. And we can look at the strain that happens, the deformation that happens in these thrust sheets. The maximum stress, sigma 1, is horizontal and roughly perpendicular to the map trace. That's because we have a horizontal stress that's causing this compression and thrusting. If sigma 1 were not horizontal, if sigma 1 were vertical, for example, we wouldn't get thrusting. Now, the perpendicular to the map trace, I'll show you in a moment. This will allow and or cause certain features to form. We can get tectonic cleavage. We can get mesoscopic folds. That's what we've been looking at so far. We can get wedge thrusts. We have seen some of those. We can also get grain scale strain. We've looked at that, just not in this chapter. It's been a couple of weeks, but you think back when we were talking about stuff in the faults rather, with like the delta and sigma style grain rotations and deformations and the little tails forming and stuff like that. That's getting down into the grain scale strain. We can also form joints. If you remember the difference between a joint and a fault, they're both cracks through the rock, but with a joint there's no motion on either side. So for a fault, the rocks move relative to each other on either side of the crack. On the joint, they stay right where they are, but it's broken now. So we can get tectonic cleavage. This is cleavage forming due to the tectonic stress. It's not formed from the formation of the rock, but purely because of that tectonic stress. You can see the beds are tilted here, so we know that we had tectonic activity going on, and then the cleavage here roughly perpendicular to the beds. We can get wedge thrusts. This is out at the leading edge of the continental slope going down the continental rise, all gravity driven from the slumping that was happening back here. You can see different normal faults, and as we continue off to the right of the screen, out here we get this detachment and these thrust faults and folding out here in the accretionary prism. We can also get them in transfer zones. Now, slip transfers let's see if I can word this better. Sorry. The transfer zone is where rock is deforming and slipping to get stuff from one fault to line up with stuff from the next fault. We've seen it in the rifts. So you have rifting and you have little transform faults to connect the rift segments to accommodate the rock movement and allow the slip to happen. We can also get it in compressional thrust fold belts. You can see here these different cross sections as we move from A to C. These little thrusts, these thrust faults, don't all line up. This thrust fault up here is short, does not reach the surface, and is about halfway across the thing. As we move down from A to the one in the middle down to B, that same fault is reaching the surface, as it does down here and down at C. However, in C, there's no other thrust faults. In A and B and everything in between, there are other thrust faults below it. So we have a it doesn't fault equally everywhere. And we saw this in those satellite images, and even in the map views. It wasn't one continuous fault. It was different ones at different, overlapping segments. Like this. So there's a whole bunch of thrust faults, some of them even going in opposite directions. Where the land to the right is the overriding plate, the hanging wall, and most of them, it's the land to the left that's the hanging wall. So lots of compression in the, from the northeast and the southwest, giving us this thrust fold belt. Now, because the primary overriding plate, or layers, the thrust sheet, is the one to the southwest, that's why the thrust fold belt curves up to the northeast. We call this the bow and arrow rule. If you take and you connect a line, a straight line, from one end of the thrust fold belt to the other end of the thrust fold belt, it creates a kind of bow and arrow look, where you have this curved trace of the thrust fold belt, and then your straight line, like we see over here on the right. And this looks kind of like a bow. If you placed an arrow on your bow, like you were getting ready to shoot your bow and arrow, that arrow is going to point in the direction of movement. So that's the direction that the thrust sheet is actually moving. So, here's the trace of our thrust fold belt. Here's our straight line, and the direction of motion is right there, perpendicular to our line and heading out into the bulge of the thrust fold belt. Here you see this curvature. If we drew a straight line across, then we would say, oh hey, the sense of motion, the thrust sheet is moving to the northeast. Two other terms to look at are salient and recess. So salient is where the belt bulges into the foreland. So it's basically the outermost part of the curve of that bow and arrow look. So in this case, the salient is right out here. This is where it's bulging out into the foreland. And the recess is out at the edges of the thrust fold belt, where the thrust faults sink down below the surface. So it's where they kind of taper off and disappear. You can see the edges of these thrust faults right along here. They're same on the other side. Those are called the recess.